All right, so good morning, everyone. So this is the second lecture in this series on Tomita-Takesaki modular theory. So the first lecture, we were just prepping and motivating uh, like the study of the structure theory of one-dimensional algebras. We'll kind of continue that. Maybe towards the end of this talk, we'll actually start talking about Tomita-Takesaki theory, but perhaps in a much simpler setting of matrices. And then, of course, most of the results of Tomita-Takesaki theory are not that helpful for matrices. I wouldn't say they're trivial results, but they're not like we have other means of understanding matrices. But then, just to understand the general framework of Tomita's theorem and the KMS condition, we'll first do it for matrices, but that is towards the end of the talk. So the previous talk, just to summarize what we did, the first thing we talked about was the postulates of quantum mechanics. And we talked about two formulations. One was the state space formalism. Yes, I have started it. Yes, thank you. So yeah, so we talked about two formalisms. One is state space, and then the other is the density operator formalism. And towards the end of the lecture, we are kind of getting towards the equivalence of these two things, and that is implemented by the GNS construction. So here, for those of you who are already very familiar with C-star algebras, this state is somewhat different from the state we mean. These are the so-called vector states, right? In the state space formalism, we have like every quantum system is governed by a state. That state is actually a vector state. In density operator formalism, we are talking about ensembles of states. So you're mixing together things. This is the one that we call states in C-star algebras. So these are the ones we call states. But then eventually we see in the GNS construction, every state becomes a vector state, right? So that was the whole point. It became a purification. Here, these were like pure states, these vector states. Then you mix things together, you got ensembles of states. Then you do some sort of purification using the GNS construction. So in terms of the mathematical formalism, both are equivalent. They are going to give you similar results, the state space formalism and the density operator formalism. But yeah, but it is much easier to work with simply because it doesn't talk about just vectors, but rather like states with certain probability distributions and so on. So this was the first thing that we talked about. And one of the key things was about talking about composite systems. If I have quantum systems A and B, so the state space is defined by HA, HP. We were talking about HA tensor HP and all of these. In fact, we were talking about examples where these were all finite dimensional. But then we started talking about quantum statistical mechanics, where you have many, many systems. Maybe they are particles, and maybe this space is C2, just qubits. So qubits. So then the state space of this composite system was supposed to be C2 tensored with itself a large number of times, which in mathematics we like to call as tensored infinitely many times. So it's like C2 to the n. And then we said that automatically, if you are interested in questions of physical interest, you are interested in infinite tensor products. We defined infinite tensor products using inductive limits of C-star algebras. And our objects were quite simple. Like the components, these were like finite dimensional things. But then once you start doing quantum statistical mechanics, you start caring about these infinite tensor products. And then if there is certain state or like in the density operator formalism, there are certain states that you care about. So this system, for example, corresponding to C to the N1, C to the N2, you had a density operator H1, density operator H2, and so on. Now you want to, and then interpreting this as space of observables, or maybe the Hamiltonians are in there and so on. Then what you want to talk about is a bigger system. So this bigger system, of course, acts on a certain Hilbert space. So you want to think of this as an infinite tensor product of Hilbert spaces. So right now, I've not concretely defined any such thing, but think of it that way. But then you want to know what is the space of observables, which are corresponding to this Hilbert space. And one thing that you want is, if I restrict that observable to any finite subsystem, then you should behave exactly like how we deal with finite quantum systems. So that is what you expect. And what is the smallest set of observables that you want? And there we made certain connections. So every state, so in this sense, we mean, so by state, I mean a positive functional, such that rho of I is equal to 1. So this is what in C-star algebra theory we call as a state. In fact, there is a one-to-one correspondence between these states and density operators. For that, to note that, all you have to do is observe that MNC actually has a Hilbert space structure using the Frobenius norm. So that norm says that if you give me two matrices A and B, the inner product that I'm going to do is trace of B star A. And of course, you can imagine the 2 norm is nothing but square root of A star A. All right. So using this, and then using Rees representation theorem for this. So Rees representation says that if I have a continuous linear functional on a Hilbert space, then it is given by certain vector. So here, let's say that vector is H. So what we are saying is rho of A is equal to H dot A for all A in MNC. So here, what does this mean? I mean, this is in this. So just interpreting what this means, we have trace A star H. But we are saying rho is a positive functional, right? That means if I input a positive operator or positive semi-definite matrix in here, what I'll get is this number has to be positive semi-definite. So H could be, yeah, so for all A, so there exists, the statement should be there exists H in MNC such that this holds. What I'm saying is by these conditions, we'll conclude that H is a density operator. So why is that? So first thing is if rho of identity is equal to 1, this implies trace of H is equal to 1. So the trace part is done. Now to prove that it is in fact a positive operator, H is positive, all you have to note is that rho of A is bigger than equal to 0 if A is bigger than equal to 0. So which is also containing the fact that A is self-adjoint. So what you have is trace of HA is bigger than equal to 0 if A is bigger than equal to 0. Okay. Right. So now from here, you want to conclude that H is a positive operator. So, I mean, either you can play around or you can assume that H is not positive. It has to be self-adjoint, first of all, because, so let's see. Yeah, I mean, you can assume H to be self-adjoint. Actually, there exists H self-adjoint, I should say. So,
how that is guaranteed?
No, sorry. So let's, no, that's definitely not true. Yeah, H need not be self-adjoint. So, yeah. So what you have is, if you look at the real and imaginary parts of H, I guess, so you have this. Then what you're claiming is trace of HA. And by the way, if I multiply two self-adjoints, that trace is always going to be a real number. So I'm not claiming that product is self-adjoint, but the trace is always going to be a real number. So trace of HA, you're saying is trace of REHA plus I times trace of imaginary part of H of A. So in this case, what you're concluding is that if this is always bigger than equal to 0 for all A bigger than equal to 0, you're in fact also saying that trace of imaginary part of H times A is equal to 0 for any A. So in particular, for any positive A, and this is just self-adjoint, then you look at the positive part of a self-adjoint operator and negative part. So, okay, let me boil it down to the following fact. So if trace of, let's say, BA equals 0 for all A bigger than equal to 0, and let's say B is self-adjoint, then B is equal to 0. That's what I want to say. The reason being, what I can do is choose B plus. You know that you have a Jordan sort of decomposition of B. So B is self-adjoint. You can just diagonalize it, diagonalize the matrix, look at the max of 0 and that function. So it's a standard technique. Then what you have is replace A with B, and this B plus and B minus also have the property that they commute, and also you have B plus times B minus is 0. So what you get is trace of B plus 1 squared, which is 0, which means B plus being a positive thing should be 0. Similarly, when you use minus B plus, minus B minus, you get a similar thing. So B plus is 0 and B minus is 0. So at least the first thing you can conclude is that imaginary part has to be 0. So you can assume, so we have shown that the H is actually self-adjoint. So by this, what we have shown is H should be self-adjoint. And using the same technique, exactly this Jordan decomposition technique, what you have is trace of HA is bigger than equal to 0 for all A bigger than equal to 0. Use H plus and H minus. Because H is self-adjoint, you do have that decomposition. Same story. What you get is trace of H plus is bigger than equal to 0, and trace of H minus is also bigger than equal to 0. But H minus is supposed to be either 0, it's supposed to be non-positive, right? So this implies H minus must be equal to 0. So yeah, that kind of tells you that H is equal to H plus. So H is in fact a positive operator. So H is bigger than or equal to 0. So yeah, the key fact to remember here is the Jordan decomposition of Hermitian matrices. For Hermitian matrices. So what we have shown is given any positive functional on MNC, it is in fact given by this density operator. Okay, so going back to our description, we had all this. So to describe the quantum system, we were like, this was the space of observables. We had C to the n, the state space, and then we had this density operator rho, and we states and density operators we have shown are kind of equivalent. But eventually, we want to talk about density operators for this big tensor product, right? Mn1C, tensor Mnkc, and so on. So you have this infinite system, and you want to talk about, and to each of them, by the way, you have associated density operators, Hk, and so on. So by this association that I just mentioned, which is quite exact, we in fact completely prove this without simplifying assumptions. So I can just say, okay, I have certain states in here, rho k, and I'm trying to build a state system on the whole space such that its restriction to Mn1C is giving you, like, for the first system is giving you rho 1. If I look at the second system, it's giving me rho 2. But in fact, if I restrict to both systems, I should get rho 1 tensor rho 2. So I want to talk about tensor products of states. So and I expect, in some sense, this will converge to some state on the big space, on the huge space that I've constructed. This, because this object we saw, we could realize it has inductive limits, but we have not really talked about tensor product of states yet. But you can imagine that that is going to be the case simply because for the moment, forget about tensor products and just think of unital star homomorphisms like this in inductive limits. And let's say you have these compatible sorts of states, meaning these connecting maps, if you compose, it's a commutative diagram and so on. So all of these are positive functionals. And if I take union of that pi infinity n that I had mentioned, so that was the map to the A infinity defined here. So if you take union of all of these, so that was supposed to be dense inside the final C-star algebra. And for the moment, for simplification, you can also assume unital embeddings and so on, because remember, the key example of interest for us was these tensor products. And tensor products will correspond to these unital embeddings, Mn1C embedded inside Mn1N2C, which is embedded inside Mn1N2 times N3C, and so on. These are all unital embeddings. So you might as well assume that for simplicity in your head. So all of these are embeddings. In order to define the product set, all you have to do is define it on this. And that is simply by just joining them together. So you define rho of A is equal to rho k of A if A belongs to, let's say, AK. So rho k is defined on AK. So if A belongs to AK, you define it this manner because of the commutativity of the diagram. This rho makes sense. Then it is bounded because these all have a uniform bound, right? Rho k of A is less than equal to norm of A, because rho has norm less than equal to 1. So rho has a similar property. So on this dense subset, it is actually having a uniform bound. You can extend it. So that extension will be called the product state of these states on this whole space. And now that you have the product state, you can do what is known as the GNS construction. And here already, I had very briefly mentioned that the rho Mn1C, so this is the density operator. But again, to convert it into, so converting to a state space formalism. So this was talking in the density operator formalism. So converting to state space formalism, all you need to do is GNS construction. So then what will happen is there will be a vector. Anyway, like I'm going to actually define and show the construction of the GNS construction. So maybe I'll put a bunch of dots here. So if you know what the GNS construction is, effectively what you get is something known as a cyclic vector, which will convert this rho into a vector state. So these ensembles will become like a sort of a purified state. Let's say, I don't want to use the word pure state. Let's say some sort of purification. That's a very common term. It's not my invention. You'll find that term in the quantum information literature also, but perhaps in just the finite dimensional case. All right. So with this in mind, we have identified that the GNS construction is an important one, which helps us go from the density operator formalism to the state space formalism. So let's review a little bit about the GNS construction. Yeah. And then we'll revisit this, because ultimately this is an example that we'll be keep coming back to, because it's so natural and it just comes from finite dimensional matrices, but the end result, the limiting case, starts giving you various examples of von Neumann factors, so-called von Neumann factors. And recall, I have not even defined von Neumann algebras yet, but still, to get until this position, I don't even need the definition. Okay, so GNS construction, as a quick reminder, is you have a C-star algebra, and I'm going to assume unital. So we'll make our life simpler. Everywhere we'll assume existence of an identity, unital C-star algebra. And you have rho from A to C. In our case, we're taking A as a MNC, the space of full matrix algebras. So this is a state, again, reminder, positive functional with rho of identity equal to 1. Okay. So one good example of C-star algebras, because Rahul asked a question about how SOT kind of naturally came about. So that is also something I'm going to answer, like maybe in the first half of this lecture. So it is always good to make this connection. Let's say you have G, a finite group. It doesn't matter whether you're dealing with C-star algebras or von Neumann algebra, especially in the case of von Neumann algebras. It's good to keep the representation theory language in mind. So I'll talk about that a little bit and then come back to the GNS construction. And I want to say that this is like a left regular representation of A. So for that, I have to mention the left regular concept of left regular representation of a group. So representations of group, you just have a map from G to MNC, a homomorphism. So MNC is supposed to act on Cn. So effectively, you're making the group G act on Cn. So rho is a homomorphism. Okay, I'm using rho for a state. So let me use pi. So pi is a homomorphism. Group homomorphism is called a representation. This is called a representation of the group, which is acting on the space Cn. So acts on Cn. Now, via this group, via this homomorphism, there is an action of G on Cn, right? So Cn becomes a CG module. So where this CG is the complex group algebra. Complex group algebra. So meaning you just formally do this. You formally look at these terms AGG, G belongs to G. These are some complex numbers. You look at the formal combinations like this, that will form a complex algebra. Then effectively, anytime you have a representation, you're representing G as a matrix. So it is acting on Cn. So via that, Cn has become a CG module. So this CG is supposed to be the analogous to A, the C-star algebra. And then you have a one-to-one correspondence between representations of G and CG modules. There is a one-to-one correspondence. So when I say A module, I mean a Hilbert space. So we'll be specializing the term to certain contexts. So in that sense, you'll actually see a lot of theorems will just be translations of theorems in finite dimensions. In particular, I'll give you a proof of the double commutant theorem without even mentioning the word double commutant theorem, but you'll realize that, okay, I'm proving double commutant theorem. So yeah, so you have this in mind, representations of G correspond to CG modules. When you're talking about sub-representations, meaning you have some invariant subspace of MNC under the action of G, these are corresponding to CG submodules. It's a one-to-one correspondence, very natural one-to-one correspondence, CG submodules. If you're thinking of this as a C-star algebra and this as a Hilbert space, then it is an invariant subspace for the C-star algebra. So that will correspond to a sub-representation and so on. Again, we'll talk about a concrete dictionary like after a little bit. But with this in mind, you have a very standard representation which contains, by the way. So one last thing I wanted to mention about this is irreducible representations will correspond to simple CG modules, meaning there are no submodules. So simple CG modules. So those will correspond to irreducible representations. Okay, so what's the left regular representation? First, you look at the group, you build this Hilbert space, or in this case, since G is a finite thing, you just build C to the n, where n is the order of the group. Then you make this vector space, so you act G naturally on this vector space. So here, the basis elements are EG. So G of EH, you just translate, you just permute these vector elements. Then of course, this every element gives you a map from L to G to L to G. I'm writing it suggestively, but you could have just written it as CG or something like that. So then this gives you, yeah. So this gives you the left regular representation of G. And the great thing about the left regular representation is that it contains every irreducible representation of G. Contains every irreducible representation of G. Representation of G. Okay, so now the GNS construction we can think of as some sort of doing left regular representation. So what you're doing is you're starting with this A. You want to make A act on itself. So you want to kind of treat this as your base, just like we built a space out of this L to G, out of this G. Similarly, we want to think of A as just being a space itself or spanning a space. By the fact that it is actually a C-star algebra, it will just span itself anyway. So you want to act it by left multiplication, but then what might happen is like in the inner product that we are going to define, then you might have some elements in the kernel, so you just mod it out. So it's just the left regular representation where the Hilbert space is given by a mod of this with respect to some kernel. So let's do that. So kernel of the state rho is defined as the set of all elements such that rho of A star A is equal to 0. And it's good to note that based on this rho, since it's positive, I can define an inner product A dot B for elements of this C-star algebra A, which is given by this. So this is a sesquilinear form. It may not be positive definite. So this kernel, for example, need not be empty. So what we'll notice is that if I look at the cosets of A under this kernel, so if I map, so I'll define this map MA, so multiplication by A on A plus kernel of rho, it will define a well-defined map. Sorry, I mean mod. Before all of this, by the way, I'll have to show that this is actually left ideal. So kernel of rho turns out to be a left ideal. So this is a left ideal, and this follows from Cauchy-Schwarz inequality. So all you need to notice is that this is just a positive form. So you have A dot B rho is always going to be less than or equal to A dot A rho. There is a square root and square root B dot B rho. So if A dot A is 0, then A dot B is 0 for any B. So in particular, if I'm looking at, let's say, CA, just parse the definition. This is what? This is rho of CA. Is this left? Sorry, B star CA, yeah, which is exactly equal to A dot C star, so CB star. So C star B, yeah, A dot C star B. You just think of this as an element and take the star of that, so that is CB star. Let me erase this. Okay. So C star B. So now using this Cauchy-Schwarz inequality, we know that this is in fact equal to 0. So that means CA is in the kernel, because CA dot B is the inner product is 0 for all B, in particular for CA. So because of that, this multiplier operator where you take a coset B plus kernel rho and send it to AB plus kernel rho, this is actually well defined. So this is a well defined map. So note that it's very similar to the left regular representation that we're talking about. But the thing is that this is may not be a Hilbert space. For example, here, what you'll have is this is positive definite. This inner product will restrict to this and will be positive definite. All I need to do is close this up and notice that M is in fact a bounded operator, so it extends to that Hilbert space. So yeah, so that is the GNS construction. So what does GNS construction say? That you have this map to some B of H. So you have pi of rho, and then you have the cyclic vector x of rho. In this case, it is nothing but identity plus kernel of rho. such that pi rho a x rho dot x rho is equal to rho of A. I mean, this is simply true by the definition of this inner product. Because pi rho of A is nothing but A plus kernel of rho, x rho is just I plus kernel of rho, and their inner product is nothing but rho of A. So this rho we have converted into a vector state here. So that is essentially the content of the GNS representation or the GNS construction based on a state on A. Okay. Yeah, so for the examples that we had, so let me just, so towards the end, I had said very hurriedly a couple of things, but let me repeat. So when we are talking about the special case of M2C, which you can think of as like qubits and observables for that qubit, like or whatever, some channels for that qubit. So the state space is C2, only two-dimensional. So you have this. As a C-star algebra, we can like we can call this M2 infinity of C, which is also called like the inductive limit that we constructed. We'll call it Glim algebra of with supernatural number 2 to the infinity. We have noticed that anytime you have this n1, n2, and so on, you'll have 2 to the whatever power, the product of all these numbers, also known as Carr algebra, the canonical anti-commutation relation. That's why Glim studied it in his, I think, in his thesis, to represent the canonical anti-commutation relations for a huge number of, I believe, is it fermions? I think so. Yeah. Yeah. Okay. So this is where we were at. And then the density operator that we are considering was use A00 minus A. Here, at least diagonalizing the density operator using some unitary, we have a good sense of what density operators look like. So at each level, you have A00, 1 minus A. You have their corresponding GNS construction where you are converting this into states, the vector states. Now the question is, what happens like when you take tensor products of these spaces? So you get a product state out of it. The product state I mentioned in the beginning. So you have corresponding a rho 1, rho 2. They actually look identical. So in fact, I can just talk about rho, and I'm talking about rho tensor rho infinitely many times. So at the end, you get the product state. And with respect to that, you can do the GNS construction, and with the formalism that we just showed, we can think of it as purifying that. But then once you do the GNS construction and you look at, okay. So yeah, okay. So I didn't want to use the word von Neumann algebra because I have not even defined it yet. But if you just even look at the algebra, look at even as a C-star algebra, you for different values of A, you get different objects. So if A is not equal to B, and let's say 0 less than B less than half, then you get different C-star algebras. So yeah, the C-star algebra given by the GNS representation of M to infinity C with respect to tensor of this rho A, let's say. Let's denote it by some notation, then MA. So if A is not equal to B, by the way, so there is a symmetry about half. You see, if I move things around, if I, instead of a 1/4, if I put a 3/4, like up to isomorphism, things are not going to change. That's why we have restricted our attention to 0 to half. Then MA is not isomorphic to MB as C-star algebras. Okay. In fact, more is true. In fact, they are not isomorphic as even von Neumann algebras. In fact, these will give you, if you look at lambda equals, is it A over 1 minus A? Is this number less than 1? Yeah, because 2A is less than 1. Yeah. So this is, in fact, if you look at the weak operator closure, whatever that is, then we get examples of the hyperfinite type 3 lambda for lambda between 0 and 1. And when you plug in B equals to half, then you get the hyperfinite type 2 factor. And if you plug in A equals 1, which means this will become 0, you get the type 1 infinity factor, which is a very familiar looking B of H, bounded operators on an infinite dimensional Hilbert space. So already this class of examples is kind of giving a lot of different sort of phenomena. So Yeah, so now we have a few examples in hand. Then is there a
Yeah, I
question?
have a question.
Yeah, please.
Yeah, if not in phenomenal algebras, like how do we see that these sister algebras are different?
Directly looking at the sister algebras, so that, yeah, I don't have good answer for that. I mean, it's still the same M to infinity, you're just using a different state as sister algebras. So maybe I'll think about it and let you know next time, our sister algebras.
Okay, okay,
Yeah.
thanks. Yeah.
Yeah.
But you are getting using the GNS representation, you are getting sister algebra.
Yeah. So GNS representation.
Sister algebra given by the GNS representation using this.
Yeah. Using this product state. Yeah. So the GNS representation gives you a sister algebra, right? Which, yeah. It gives you a sister algebra. What I'm saying is the end result. Maybe it's the correct statement.
What is this? GNS representation is your sister algebra positive linear means you get the inverse space and the
right.
the vector. If you are positive linear, you will get
Yeah. So the GNS representation is a representation of this. So you have the image of that representation. So maybe I should say MA.
So that means
image
of the sister algebra
of the GNS. So image of M2 infinity C under the GNS representation.
So the Hilbert spaces are changing, right?
Yeah, the Hilbert spaces are changing. Yeah, the Hilbert spaces are changing. So the Hilbert spaces are changing. So it's not exactly.
MA is acting on some basis.
Right. MA is acting on a much bigger HN, which is like. Right. Yeah, it's acting on a different sort of Hilbert space. You cannot even think of it as taking the inductive limit of C to the 2 to the n. So initially, like a priori, you had, okay, M2C is acting on C to the n, C2, then another copy of C2 and so on. When you're talking about the tensor products, naturally it was acting on certain finite tensor products of C2. But there, after you have made that construction, now you're identifying this product state rho. Then based on that, you're doing a GNS construction. Now you have a new Hilbert space. And you have this homomorphism from this space to there. And then you're looking at the sister algebra there. So there.
Sister algebras are same, but the phenomenal algebras are
Oh yeah. That's what I was thinking, because this is actually a faithful representation. So as sister algebras, they should be isomorphic. So I scrapped this actually. I oversimplified. Yeah. So Raja suggests that the sister algebras are actually so, and that would be a consequence of the fact that at least when A is not equal to 1 or 0, at least in those cases, you'll get faithful states. And these are all faithful states, by the way, when A is not equal to 0. And then you will get faithful representations out of these states. So yeah, so I take that back. So MA as von Neumann algebras, this will not be isomorphic as von Neumann algebras. Okay. All right. But as sister algebras, M2 infinity, it will be actually isomorphic to M2 infinity. So yeah, thanks Shankar for pointing it out.
And are you claiming that for different values of A,
Yeah. So what I'm saying is actually these are examples of what are known as the powers factors. So these are the powers factors. This MAs, these are known as powers factors. And these are actually somewhat around the time Tomita-Takesaki theory was done. It is a little bit pre-Tomita-Takesaki theory, 1967. But what I'm saying is already a lot of things like type 3 were already naturally appearing even before we had a good structure theory. So just purely if you're interested in the structure theory of von Neumann algebras, type 3 is of course like something that you want to understand and classify. But even even otherwise, the natural examples that you're getting from physics are all like a lot of them are type 3 lambda, at least in this case, where you're looking at density operators and everything has to be of this form, up to unitary equivalence. And most of them are type 3 lambda, right? Only one case you have A equals half giving you type 2 1 infinity, 2 1, the other case giving you type 1 infinity, but rest of it is type 3 lambda. And by the way, if you keep changing this and density operators, the general class, you get the Araki-Woods factors. There also you observe that most of them are like type 3 factors. So that's why you will see this phrase written in many textbooks. I mean, the justifications maybe you can find in the original papers, but generally they don't explicitly say this, but it is just coming from looking at quantum statistical mechanics of like large number of particles. Okay. So yeah, as von Neumann algebras, they are not isomorphic, but as C-star algebras, they are just isomorphic to the Glimm algebra or the Carr algebra, so to say. Okay. So now, having used the word von Neumann algebra many, many times, we are hoping to come back to the definition of a von Neumann algebra. But instead of defining von Neumann algebras, what we'll do is actually discover von Neumann algebras. We'll say that, okay, it's a very natural definition to consider. So for that, we have to go back to that association I mentioned about representations of G and CG module. Of G, there's a one-to-one thing like this. And you may have encountered this result saying that every representation of a finite group is a direct sum of irreducible representations, which is just saying that every CG module is direct sum of simple CG modules. Such a thing is known as semi-simple. So if you have a ring R and you have a module over that ring, it is said to be semi-simple if you are able to write it as a direct sum of simple R modules. So yeah, this will answer Rahul's question about strong operator topology. The reference I'm using is chapter 17 of the Lang's book on algebra. So chapter 17. So Serge Lang, algebra. So this is just before the representation theory of finite groups. Okay, so with this as motivation, we'll replace this CG with R, and we'll be talking about semi-simple modules over a ring R. So R is some unital ring. And M is a fixed R module. So if you are kind of trying to think ahead, think of R as being a von Neumann algebra and M as a Hilbert space. R is acting, the von Neumann algebra or whatever your algebra of operators is acting on the Hilbert space, making it a module. So you have a fixed R module. Then first of all, we have a ring isomorphism. So this is just a lemma sort of thing I want to note. Between this and matrices, so this is m by n matrices over endomorphisms, end Rm. So what is this? This is the endomorphisms, meaning these elements of this look like map from M to M. So it's a linear map. So R linear map. So phi of R dot X is R dot phi X. I'm just collecting all those maps. So what I'm saying is there is an isomorphism like this. So how is that isomorphism given? It's actually quite straightforward. Like when you have a map, so this is R endomorphism from Mn to Mn, right? Now I have natural maps, injection maps like this, phi I and pi j, projection map to M like this. So here what I'm doing is taking an element here and injecting into Mn, where rest of the entries are 0. And here what I'm doing is annihilating rest of the entries and jth only I'm considering. So if I have a endomorphism psi here, then pi j composed psi with phi I is actually a map from M to M. So this belongs to end Rm. So this is in fact giving you the entries of this matrix. So this is just like we're just generalizing the idea of matrices where like all those components inside the matrix are acting independently on each of the elements of that vector space. Here you have a module, R is acting on this module. So this kind of immediately tells you that I can think of end R of this module Mn, M to the N, as being isomorphic to matrices over this. Okay, so think of this as a short lemma. So now I'll mention what is very commonly known as Schur's lemma. So Schur's lemma says that if you have E and F, these are simple R modules. Simple meaning there is no proper submodule. So you have simple R modules. So that is not equal to 0, not trivial, and has no non-trivial submodules. No non-trivial submodules. Again, think of R as von Neumann algebra or algebra of operators R module. Simple, meaning it has no sort of common invariant subspaces. So it is kind of, yeah, so simple R module, yeah, it doesn't have any invariant subspaces. Okay, then Schur's lemma will tell you that this ring is a division ring, meaning all the non-zero elements are invertible. So every non-zero element, it's actually almost like a borderline tautological statement. It just follows from the fact that it's a simple module. So every non-zero element is invertible. So why is that? Proof: I take any endomorphism from E to F. So this is a R module map. So kernel of phi is an R module naturally, because if phi of x is equal to 0, this implies phi of R dot x, which is R of phi dot x is 0. So this is in fact like sort of R invariant. So kernel of phi is an R module, and image of phi is an R module. In fact, it's a submodule of E. This is a submodule of F. So what that is telling you, either kernel F is 0 or the whole thing. So if kernel F is 0, then it is an isomorphism, because image of F, first of all, is not 0, so it must be equal to F. So you're using the fact that both E and F are simple R modules. So that will tell you that phi is an isomorphism. If phi is not the 0 map, phi not identically 0 implies phi is an isomorphism, is an R module isomorphism. So which tells you that there is an inverse. So every non-zero element has an inverse. So this is a division ring. That is Sturz lemma. Okay. So a quick definition. So semi-simple R modules are by definition are direct sums of simple R modules. This is definition, but it is actually equivalent to saying the following fact: if E is a submodule of F, or let's see, so F is a submodule of E. So E is semi-simple. If this is the case, this is a theorem that one has to prove, but what happens is you always have a complementary submodule. So E is equal to F direct sum F prime. So in a sense, it is saying that if my von Neumann algebra has an invariant subspace, there is a complementary invariant subspace. I'll write the dictionary explicitly at the very end. So just to kind of clue you in, so this is where we are headed to. So from now on, we are going to talk about semi-simple R modules, which are direct sum of simple R modules. So if you have a semi-simple R module, then you can define R prime as this. So this is the ring of endomorphisms, end RE. So ring of endomorphisms. In the case of simple, we saw that this was in fact a division ring. That was Sturz lemma. So R prime is end RE. This is called the commutant of E. R. So why is that a commutant of R? Simply because if you think of, so for any alpha in R, I can associate a map F alpha from E to E. How is that? I send X to alpha times X. So to any alpha in the ring R, I associate alpha. Then when I'm saying phi inside here is a R module endomorphism, I'm saying phi of alpha X is equal to alpha phi X, right? That is the definition, which in this notation is phi composed with phi alpha acting on X is equal to phi alpha of phi acting on X, where X is the element of this module, element of the Hilbert space. So phi and F alpha are kind of commuting. All right. So this is the commutant. Then we have something called the bicommutant. So by the way, E is an R prime module also. So where R prime, remember, is end RE, it's the ring end RE. So E is an R prime module. Okay. So what, given phi, I have to tell you the action, right? Action. But the action is quite straightforward. Phi is here, X is here. All I have to do is phi of X. Phi is an endomorphism of E, right? So you have phi of X. So E is an R prime module. So then I can talk about the double commutant, right? End of R prime of M, just like I did with end Rm, since E is also an R prime module, I have this. Then we are led to something very nice. So this is, by the way, called the bicommutant or the double commutant. So double commutant of R. So the question, this is the question that we will answer with the next lemma or two. So first of all, notice that R set insets are double prime. So by the map, alpha goes to F alpha. So, so simply because of this fact, so you can think if this is an element of R prime, right? So yeah, what I'm claiming is F alpha belongs to R double prime, which is equal to end R prime E. So why is that? So for that, I have to say so F alpha of phi dot x, alpha dot x, right? Which is true. By definition, this is phi of x, this is phi of alpha. Yeah, it's exactly, just have to stare at it very carefully. Then you notice that this identity is also telling you that F alpha is in R double prime. So you have this natural embedding of R into R double prime where alpha is sent to F alpha. So now the question is, it has an image inside this. It's again a ring. Identity will of course go to the identity map. So this also, the image is also unital and so on. So question is, how big is the image of this map? And the answer is given by the Jacobson density theorem. So in my email, when I was trying to answer Rahul's question, I did mention that. So today we are explicitly seeing that. So I'll say that in two parts. Both of them maybe I will call Jacobson density theorem. So let M is, so I'm changing my notation from E to M again. So semi-simple R module. R prime is end RE, Rm. And let's say F belongs to the double commutant, which is end R prime of M. So I want to say that F is actually, although it may not be in R or it may not be of the form F alpha, we know that R is sitting inside R double prime. So it may not be sitting inside, but it can be approximated in a certain way. So let X belongs to M. Again, think of this Hilbert space. I'm choosing a vector in the Hilbert space. Then there exists alpha in R. This is the assertion of this theorem. Then there exists alpha in R such that alpha of X is equal to F of X. I'm not saying alpha is equal to F or F alpha is equal to F, right? That is what I want to say. If I really want to say that the double commutant is actually exactly like this, but what instead I'm saying is, if you give me any vector, F of X, wherever F sends X, I can actually implement that using an element of the ring R. Now, as a quick corollary, so yeah, so okay, before the corollary, let me prove this. So proof is quite short. Again, like if you go through this, it looks very, very like elementary straightforward, but of course it took a long time to like clean up this language. Now choose that vector X, look at the module generated by this, you get Rx, but this is semi-simple, right? This M is semi-simple. So then there is an N such that M is equal to Rx. There is a complementary invariant subspace, complementary submodule. This is the subspace generated by this. In fact, if you're thinking of von Neumann algebras, we no longer care about invariant subspaces. We care about closed invariant subspaces because we are talking about Hilbert spaces. We want sub-Hilbert spaces, that means closed subspaces. So typically at this stage, the proof will be replaced by Rx, closer of the span of this. So if you remember your proof of the von Neumann's double commutant theorem, you may recognize this step. But anyway, keep that aside. Here we are doing a precise proof. M is equal to Rx plus N, and there is a projection map from M to Rx. Projection map is simply given by, you just ignore whatever is in this part. You just send it to 0. This is a projection map. In fact, it's a endomorphism. It's a linear map, and it's so pi belongs to end Rm, which is R prime. So why is that? So for that, simply I have to check that it's a R linear map. So pi of R of X. So if I have x, so okay, let me not use the, since I used it, x is fixed, let me use v. So if I have any v in M, by this decomposition, I can write v as some r1 x plus some y, right? Now, if I multiply any r to this, in fact, the decomposition is given by this plus r dot y. It is like this. Now, if I apply pi here, pi r dot v, it ignores this part, which is in n. So what it gives me is r dot r1 x, which is nothing but r dot pi of x. So we have shown that pi is in fact in r prime, it's in the commutant. So hence, f of x is equal to f of pi x. Why is that? Because simply because x is in Rx, right? R is a unital ring, so x is in Rx. So this equality is just at the level of x equals pi x. So I'm just applying f on that. Then using the fact that f is in the double commutant, so since pi is in R prime, so you can move things around, pi of fx. So this implies, since fx is equal to pi of fx, this implies fx belongs to Rx. It's already in the subspace where you're projecting onto it. The image of pi, remember, is just Rx. So this is exactly the statement. This implies there exists alpha in R, such that f of x is equal to alpha of x. So we proved the lemma for one vector. Now, so the first thing I mentioned, remember, is this fact, this isomorphism. We are going to use it to just give a simple induction argument to prove it for n vectors. So let me state it that way. So again, same setting. M is a simple R module and so on. So let x1, x2, xn belong to M. And F is in the bicommutant. Then there exists alpha in R such that alpha of xi is equal to fxi for I equals 1 to n. So there we had just one element. Here we have n elements. So what we are saying is that f may not be in my R, or it may not be of the form f alpha. But if you give me finitely elements, I can always find an element f alpha where both of this alpha and this f are matching on that finite dimensional space. Here, of course, I'm not talking about a vector space. This is like, but that is roughly the intuition that we should have in mind. So here, all you have to do is look at the action of R on this module Mn, and then look at the vector x1 up to xn and treat that as our x. So we can use the previous lemma, in fact, immediately to give a proof of this. So your new module is m to the n, and all you have to note is end Rm to the n is, that's the first thing that we mentioned, end Rm. And also note that m to the n is semi-simple, because m is semi-simple, m to the n is also semi-simple. Because if m is a sum of simple modules, then you just keep adding the other, like some sort of multiplicity. So by the definition that we used, we have this. Then you define this new map, m to the n. So it is very related to f. It's just component-wise applying f. So what we have is fn belongs to end Rn prime of m to the n. So here Rn so notation wise, so what am I trying to do here? So I want to say that Fn in fact belongs to this double commutant, right? Mtn and Rm bicommutant of this. So this I can call as Rn. So yeah, so it's mostly exercise in parsing notation. So maybe better to use a notation Rn, because think of this as my module, right? So this is Rn prime. Yeah. So Fn belongs to end Rn prime of n to the n. So that is simply because whenever I'm yes, so you have Rn prime endomorphism. So if you're looking at something like F alpha, so F alpha to the n, which is nothing but you just multiply alpha dot y1 and so on. So yeah, this is in fact going to be isomorphic to and to R. Yeah, this is going to be isomorphic to R. Not R, that's not what I mean. But yeah, just give me a second. So you're defining this map Fn. So component wise, you're applying F. So using the first thing we said, you have end R of m to the n is just matrices whose entries are endomorphisms of m. Then when we're looking at the bicommutant of R, like, or rather, I should say it's not really the bicommutant of R, but with respect to this module M, the R module action. So here we have replaced with M n. So now Rn double prime is in fact isomorphic. Yeah. I think this is what I was trying to get at. This is isomorphic to end R prime, end Rm, right? Okay. So this should be a consequence of F belonging to end R prime of n. Yeah, these two should be isomorphic. Yeah, okay. I mean, so maybe you can, it's a very simple computation. It's just that you have to sit down for 2-3 minutes and do it carefully. But once you have this, you use the theorem in this context. So you have Mn semi-simple module and you have this map Fn. And the R is still the same. You're still embedding R, and that is happening component-wise, R dot y1, R dot y2, and so on. So in that case, what you get is F of n, this, there is a F alpha such that this holds. So which means F of x1 is equal to alpha x1, the same alpha, F of xn is equal to alpha of xn. All right. So modulo those small details, small but important details, we have this Jacobson density theorem. Now, if we follow through this proof of this theorem and make these substitutions. So before that, let me mention a dictionary. So here's my dictionary. So now we'll specialize a little bit, semi-simple C algebra, meaning complex algebra A. Here you have so-called von Neumann algebra. Here you have M is an A module. So von Neumann algebra R. So you have Hilbert space H is R module. Of course, these are a little bit sloppy terms, but good to keep this kind of analogy in mind. Now this end A of M, so A module endomorphisms is the commutant of this. So this is supposed to be commutant. And then M is submodule of, so by the way, A acts on itself as by the left regular representation. A acts, so A becomes a module by left multiplication. So this means what I'm going to explain, that R has a cyclic vector. So being a submodule of the regular representation kind of tells you that R has a cyclic vector, R has a separating vector. So if it contains the left regular representation, some sort of, the analogy is R has a separating vector. And if you have this, so M looks like the left regular representation, then R has both, has a cyclic and separating vector. This is an assumption that you'll see very commonly in the operator algebras literature, that let R is represented on a Hilbert space with a cyclic and separating vector. That just means that immediately the imagination should go that, okay, R is like a left regular representation of something. So whatever techniques you have there, you maybe, so that's why it's a quite reasonable assumption to make in many different settings. And like I said, for the group case, all the irreducible representations are contained in here. I'm not saying an exact theorem like that holds, but the intuition you can use to transfer results back and forth. Okay, so now with this analogy in mind, let's say I want to talk about representation theory of non-compact groups and so on, where you don't really have, let's say, like nice theorem like Peter-Weyl theorem or anything. One example could be the real line, where you're talking about one parameter groups, unitary groups, and so on. So you do want to talk about representations of non-compact groups. But in that case, finite dimensional spaces don't suffice. You want to go to infinite dimensions. Then you want to see which of these phenomena actually survive. So now, if you look at this density theorem, the Jacobson density theorem, if I retrace the proof, I use the language of Hilbert spaces and this algebra of operators. Don't use von Neumann algebra, use star algebra of operators. So I'm thinking of M as being the Hilbert space and R as being a star closed algebra of operators. I keep doing this. I pick a vector X, I do this. Now, instead of what was the conclusion here, that there exists alpha such that fx equals alpha x. But if I replace this with this span closure, my conclusion right here is not equality, but it's saying given epsilon bigger than 0. So given any epsilon, there exists alpha in R, alpha epsilon, depending on epsilon, such that alpha epsilon x minus fx is norm is less than epsilon. So to repeat, so you had something in the double commutant. Then you are saying there is something in the original commutant which is closed on this vector. And then the main Jacobson density theorem tells you that you have epsilon bigger than 0 and you have a bunch of vectors x1, xn, x1, x2, xn. Then you want to say there is some epsilon such that alpha epsilon dot x minus fx I. So alpha epsilon xi minus fxi is less than epsilon. So effectively what you're trying to say is that, okay, I may not have this equality that f is implemented by alpha, but if you give me finitely many vectors, I'm always able to implement by this. So what sort of notion of convergence does this give me? If you think about it, it exactly gives you strong operator convergence. So if you're, and then that kind of naturally leads you to strong operator topology, and no surprise, you get the double commutant theorem, which is the Jacobson density theorem in its infinite dimensional manifestation. Okay, so I'll conclude that. So I'll define von Neumann algebra in the following manner. Von Neumann algebras by definition are things that behave like the way we want, keeping the Jacobson density theorem in mind. So, okay, so let's say you have H is a Hilbert space. So von Neumann algebra, VNA, is a star closed subalgebra of the set of bounded operators on B of H, containing IH, meaning the identity operator on H, containing IH. So von Neumann algebra by definition is a star closed subalgebra of B of H, closed in the strong operator topology. And strong operator topology just means, so in that notion of convergence, we have Ti goes to T if norm of Ti minus, so Tix minus Tx goes to 0 for all x in H. This is the definition. You can translate this back into like fundamental system of neighborhoods of 0, like the 0 operator and so on. But effectively, the idea is pointwise convergence. So this is pointwise convergence. So topology of pointwise convergence. So Ti goes to T if for given any vector x, Tix goes to T of x. Then if I mention the double commutant theorem, by now it's already, this is equivalent to saying that R double commute. So if VNA R is a star closed subalgebra, this is what we just proved in the Jacobson density theorem. Because we are able to approximate, and if we assume that it is already closed in that approximation procedure, then it has to be equal to its double commutant. So this is what we mean by a von Neumann algebra. Okay. And we have seen various examples, but one of the motivations, initial motivations of von Neumann was, of course, like to mimic representation theory of finite groups or compact groups. And at that time in the 30s and 40s, of course, this was also a very, very active field. And you can imagine Jacobson and these guys, sure, they're working in the 1910s, 20s. So the ideas were floating around. So he was trying to push these results to infinite dimensions. So the first consequence was the double commutant theorem. And then another consequence that he wanted was Artin-Wedderburn theorem, which is again an immediate consequence of the Jacobson density theorem. So he wanted an analog of this. So what does Artin-Wedderburn theorem say? And it's, yeah, like I said, it's a very straightforward consequence of Jacobson density. It says if I have a semi-simple C algebra, I'm stating it in a more specific context. No need to go in the most general. So think of a semi-simple C algebra. or even more basic, simple C algebras are isomorphic to MNC. Simple meaning it doesn't have any, let's say, non-trivial ideals, two-sided ideals. So simple C algebras are isomorphic to MNC. So Artin-Wedderburn theorem says that, and semi-simple. So in the general, by the way, I'm missing a few terms. I should say simple finite dimensional. I should say finite dimensional. So we're being sloppy, but yeah, these things can be taken care of. So semi-simple finite dimensional C algebras, complex algebras, are isomorphic to direct sum of some MNC. So von Neumann thought, okay, I want to prove such a result. So in a way, the language wise, you want to think of von Neumann algebras as being semi-simple rings. Semi-simple rings are those rings where all the modules on that ring are semi-simple modules. So he wanted to think of infinite dimensional semi-simple rings. Now, if we are, or semi-simple C algebras, let's say. So now if we're using this analogy, he wanted to prove the following theorem, that it's actually, he wanted to prove the Artin-Wedderburn theorem that the simple von Neumann algebras, so what von Neumann wanted to prove is that every von Neumann algebra is isomorphic to MNIC plus some B of H. So you're saying that the only difference that you'll get is, okay, here you have matrices, there you'll have bounded operators in Hilbert space. So this is what he set out to prove. But of course, very soon he realized that's not the case. You have many, many examples of von Neumann algebras, of course. I mean, if that were the case, then it probably, I mean, he wanted to just wrap it up and get done with. Like, he's like, okay, I proved that the semi-simple algebras in the infinite dimensional case is B, or simple algebras in the infinite dimensional case is B of H, and I'm done. But then he very immediately realized there is something like a type 2 factor. So those are examples of these semi-simple objects which do not fall into this sort of classification. So then he immediately realized, because double commutant theorem he proved in 1930, very, very close to when he was writing his book on foundations of quantum mechanics. But around 32, 33, he started realizing that, okay, I mean, the semi-simple objects in this kind of rings of operators is actually quite vast. And in 36, he starts his study of what we now know today as von Neumann algebras. He writes his very seminal papers on rings of operators. He recruits Murray, and then he realizes that it's actually a very, very rich world. There's a lot of other kinds of phenomena that is happening. So he wants to study all of that. So again, I hope you by now have a good grasp of what von Neumann was trying to do and why he was inventing these theorems, density approximation theorems. Okay. So then the next thing was to study the simple objects, right? So simple von Neumann algebras are also known as factors. So are called factors. And semi-simplicity means that it is sum of factors, right? Direct sum of factors. That should be the case. But here, of course, it is expected something like that should happen. But generally, what would happen is that every von Neumann algebra will turn out to be direct integral of factors. Of course, you have technical assumptions like they are represented on a separable Hilbert space and so on. But what I'm saying is the same ideas that we had from representation theory, where we are saying that every representation of a finite group is direct sum of irreducible representations, which are like the simple modules. So the same ideas we are trying to push forward, but then of course we are faced with many difficulties that are given by the infinite. So mostly analytic difficulties that we face. So yeah, so anyway, it's not a very simple case, but we do have something similar like direct integrals. Okay. So since I mentioned these words type 2, type 3, and I never really talked about what they are. So like I said, I had not even defined von Neumann algebra, but so now that part is taken care of. So here I want to, so why are type 3 factors? So I'll put in parentheses, supposed to be scary. So it looked like they come up naturally if you are interested in physical problems, but why are they scary? So they're scary, at least before we had Tomita-Takesaki theory, they were scary because it was like the structure theory, we had very little idea. And part of the reason was we did not have a good dimension theory of this. Okay. So here, I want to talk a little bit about dimension or comparison theory of projections. In a one-Neumann algebra. So like a quick recap. And this will already tell you that if we care about comparing projections, and projections, when you think in terms of one-Neumann algebras, you should think of a projection E, projection, like an event. It's like an event. In probability, you have this sample space. Then if you choose, of course, there will be technical details like, okay, there has to be sigma algebra on that, and events are elements of the sigma algebra, but roughly think of it as you have a bunch of points that, so any subset of this sample space is like an event, right? But when we are talking about quantum mechanical events, we actually are talking about, let's say, function spaces on this. And let's say there are finitely many points. Your sample space was finite, and you're talking about finite subset. So in the quantum mechanical sense, you have a Hilbert space of dimension, however many points you have, and you're talking about a subspace. And subspaces are corresponding to projections. So events in quantum mechanics correspond to projections. Now, if I want to say a projection is bigger than the other, I typically want to say that this event is more likely than the other. So if I'm comparing events in probability, I'm trying to say one event is bigger than the other. So that is kind of the base of this comparison theory. So effectively, I want a dimension function which has properties resembling this. Like dimension of E plus F, if we have orthogonal projections, should be like dimension of E plus dimension of F if A and F are orthogonal projections. So they're like independent events. So the probabilities that you're talking about, they kind of, you can add them up in a sense. And of course, if you have E less than or equal to F, then dimension of E is less than or equal to dimension of F. And then if E can evolve to F, then you want to say that they are like similar probability events. So some sort of isometry is there, which is sending E to F. That isometry, which is being recognized by your set of evolutions, or your, I would say that is being recognized by your one-Neumann algebra. So these are the rough ideas that kind of kickstarted the whole thing. But before I talk about Murray von Neumann equivalence and comparison theorem, one lemma, small lemma from matrix theory. Let E be a projection matrix. Then trace of E is equal to rank of E. And that is simply because these rank and trace are unitary invariants. So you have this is equal to trace of E, rank of UE, U star is equal to rank of E. And without loss of generality, I can diagonalize it into this. And for this, it is true that trace is exactly the same as rank. Rank is n if there are n entries 1, and trace is equal to rank. So we do have that if I have a projection, then rank of that projection or sort of dimension of that projection is equal to trace. So in a way, if I want some sort of dimension theory, I do care about some sort of like trace being there on that one-Neumann algebra. And just to give you the secret away, why are type 3 factors scary? That is because any sort of trace you try to build on a type 3 factor can only take values 0 and infinity on projections. So in a way, you have nothing to compare. Unless it's a trivial event, all events are kind of extremely big. So you're not able to do some sort of comparison. So that's why even like B of H, not everything is a trace class operator, right? Identity itself is not a trace class operator, but you still have some semblance, like the trace class is a big set inside it, and you can use those sort of techniques to glean something about general operators and so on. But in type 3, you don't even have any sort of trace, so to say. So that makes them scary. There is no dimension theory. And that's why it was almost thought impossible. And that's why Tomita-Takesaki theory is supposed to be a miracle. Okay. So let me say a few words about comparison theory of projections in a one-Neumann algebra. So concrete words. Comparison theory of projections. So let's say E and F are in a one-Neumann algebra R. I'll say that E is less than F. So this is the Murray von Neumann equivalence. Yeah, sorry. Before that, I want to say E is equivalent to F if there is a partial isometry. So isometry just means it will map things preserving their lengths. Partial isometry means that on a subspace it is doing that, on the complement of that it is just vanishing. So there is a partial isometry V with initial projection E and final projection E and final projection F. Okay. So what does, again, to repeat what a partial isometry mean, is that corresponding to a projection, you have a closed subspace of the Hilbert space like this, and there is a complementary part. So this is like E of H, and this is like I minus E of H. And then similarly, you have F of H here, and then whatever, like this part I don't care about. So what this partial isometry is doing is mapping this part in an isometric fashion. So this is an isometry. Now this part, it is just sending to 0. Let's say 0 is sitting somewhere here. This part is just collapsing. So that is a partial isometry. So it's kind of giving you the comparison between E and F. It's saying there is an isometric map. And the important thing is here, so partial isometry V in R. So can R see that equivalence? So then E and F, so this is a relative concept. E is equivalent to F with respect to the von Neumann algebra R. So E and F are in R. So this kind of gives you an equivalence relation. Then we'll define a like sort of partial order. I don't want to, so partial order has this property that if E is less than equal to F, F less than equal to E means E equals F, right? So I want to mod out this equivalence relation. So modulo that, this will become a partial order, but I will define this symbol. So E less than F if there exists G in R such that G is less than equal to F and E is equivalent to G. So essentially there is a partial isometry which will send E to something which is contained in F. So then, so on the equivalence class, so equivalence class with respect to this Murray von Neumann equivalence, this forms a partial order. This thing forms a partial order. This needs a proof, of course. I'm not saying that this is a trivial statement, but I'll not be doing it. It's very set theoretic in nature. If you once you have this model in mind, in classical probability, you have a sample space and you have these events and so on. Then here you're talking about projections being events. So what this is trying to tell me, oh, I lost my thought. Yeah, I forgot what I was trying to say. Okay, anyway, like maybe it will come back to me. But anyway, so this, yeah, oh yeah, I just remembered. So this is very set theoretic in nature. So in the sense, for sets, it is easy to see that if you have like, if I have AI has cardinality less than BI and so on, AN. Yeah, so if you have a collection, could be an infinite collection. If the cardinality of AI is less than cardinality of the BI, then unions have the same property and so on. If you have disjoint sets. So similarly, if you translate it into the language of these projections, you will have, if you have an orthogonal family, then summation, and each of them is less than equal to the corresponding FA. So EA, orthogonal family. So if you draw the analogy, then it being a partial order will follow from the Schroeder-Bernstein theorem, using the same sort of analogies. If A is a smaller set than B and B is a smaller set than A, then A and B have the same cardinality. That's what Schroeder-Bernstein theorem says. So similarly, you will have a conclusion that if E is less than equal to F, F less than equal to E, then E and F must actually be equivalent. So it needs a proof, but this analogy helps a lot. So FA also orthogonal family. Then EA is less than FA, then you have this conclusion. So this is the conclusion. All right. So I'm going to assume this fact that this actually forms a partial order. And then I'm going to talk about something known as finite projections. So projection E is said to be finite if it is not equivalent to any proper sub-projections. If it is not equivalent to any proper sub-projections, very similar to how a finite set cannot be in bijection with a proper subset. And infinite similarly is that if there is a proper sub-projection to which it is equivalent. So similarly, E is infinite if it is equivalent to a proper subprojection. Okay. So good thing is finite projections kind of have like finite dimension. You could think of it that way. Infinite projections cannot have finite dimension. So in that sense, having a lot of finite projections is quite helpful in, like, even though B of H identity is not finite. So in that case, simply because of cardinality reasons, you can take any. So you have this orthonormal basis, let's say E1, E2, En. Then you take any infinite E4, the even numbers. So look at the span of this even number, span closure of this, E6 and so on. So span closure of this. Then this gives you a projection onto that, right? So if you look at the projection onto that, in B of H, these two are actually equivalent projections. So I, although it is strictly bigger than E, these are equivalent projections, simply because you can draw an isometry, just doing a bijection or set bijection of this orthonormal basis, and then just building up a unitary or building up an isometry out of it. So I is not finite, but you have these finite rank projections. So you do have a bunch of these finite projections in B of H. So still, you are able to make use of the finite, like matrices, whatever intuition you gain from matrices, to maybe guess about what happens in B of H. But in type 3, so I'm always keep coming back to type 3. So the only finite projection in type 3 factors is 0. In fact, it's kind of defined by exclusion. So factor is of type 3 if and only if it does not have a finite projection. So you can in fact use it as a definition. A factor meaning a simple von Neumann algebra, in the sense that I said it has trivial center. So VNA, von Neumann algebra with trivial center, is of type 3 if it has no finite projections, no non-zero finite projections, let's say, no non-zero finite projections. Okay. So this is kind of a good point to at least understand, okay, these were exotic objects from the get-go. So type 2-1, remember I mentioned something like, if you had this M2C using the density operator 0, 0, half, what is the state corresponding to this? That is the trace, right? The density, if you take the density operator half, 0, 0, half, that is the trace. And then when you're taking this infinite tensor product, you will actually get a tracial state on the car algebra. You'll end up with a tracial state there. And then if you do the GNS representation there, and you take the weak operator or strong operator closer, what you'll end up with is a hyperfinite type 2-1 factor, right? So this, which is quite distinct from the usual matrix factors that you are familiar with. So in that case, already, so already we have a sense of this type 2-1, although again, they're infinite dimensional objects, we have certain sense. But for type 3, you are not able to build up any sort of trace. So I just, because I don't want to spend too much time on comparison theory, I hope the general idea I have gotten across, that it's about like looking at finite projections, and type 3 are very exotic objects. They don't have finite projections, so you cannot really assign a dimension function to it, a non-trivial dimension function. So comparison becomes much harder, and you cannot even use certain techniques where you can like transform an operator and make it certain like a finite rank sort of thing, and so on. So those sort of techniques are also not available in this case. So Then to describe the structure theory of type 3 factors, the big breakthrough was to realize them as type 2 infinity cross product with some one parameter automorphism group on this type 2 infinity. So type 2 1 and type 2 infinity, the analogy you can think of as just matrix with B of H. So type 2 infinity is like tensor of type 2 1 with B of H. So you put you build a big matrix and all the entries, an infinite matrix. And for B of H, you put complex numbers in here, right? For B of H. But if you're talking about type 2 infinity, you put elements of a type 2 1 factor in there. So if you have a bounded operators on a Hilbert space and you're trying to think of it as a big matrix, infinite matrix, then all the entries either you can think of as being complex numbers or you can think of as putting matrices in there. And similarly for type 2 infinity, you just think of us putting elements of a type 2 1 factor in there. Of course, there's no unique type 2 infinity. The classification problem is still open. But at least type 3, we have a sense that, okay, it boils down to classifying type 2 infinity and certain, not all automorphism groups will work, certain one parameter automorphism groups of type 2 infinity. So this was the great success of Tomita-Takesaki theory. And next time, so this is a good place to stop. So next time what we are going to do, so maybe I'll mention a very small anecdote and end with that. So next time I want to talk about Tomita-Takesaki theory for MNC, because what we have been doing throughout has been trying to motivate ourselves by very, very carefully looking at phenomena that is happening in MNC. So this reminds me of an anecdote which I'm going to share with you. So this is what we are going to start next time. Next couple of lectures, we'll talk about Tomita-Takesaki theory on matrices. So the Tomita's theorem and all that we'll prove for matrices, and then we'll see that it just transfers to the general von Neumann algebra case with cyclic and separating vectors and so on. So the anecdote that reminds me is one I heard from my former supervisor. So a bright young man from India. So this is from the 70s, and I'm sure all of you know him. So he goes to the US, he works with Paul Halmos. And at some point, he has this idea that he wants to write a small book on Tomita-Takesaki theory of MNC. Anyway, like this story I'm trying to tell you is something I heard. So take it with a pinch of salt. So no ways to corroborate. So he decides that he wants to write a book on this. Then Halmos comes to Cadison and he says, okay, like, what do you think? Is this a good idea? Then Cadison says, okay, it's like doing calculus on discrete spaces. So it's going to be utterly useless. And from then on, the story is that like after that, any conference they met, Halmos just walked away. Like he would never talk to him and so on, because he was, like he said, like I didn't think there was anything to do talking about Tomita-Takesaki theory for MNC. And by the way, the person I'm talking about is V.S. Sundar. So many people in the audience may know him. He's like one of the star operator algebraists from India. So yeah, this is a hard story. So if you want to confirm, maybe you can talk with Sundar. But the idea is that I think I disagree with my supervisor here. So we'll see at the end of my talk. I think both statements were wrong. First of all, doing calculus on discrete spaces is not such a bad idea. So that anyway, like you can build function spaces as inductive limits of like finite dimensional function spaces or finite dimensional Banach spaces. So on that count, I don't agree. In the second account, I do think there is something informative to learn about doing this modular automorphism group, looking at the K-mesh conditions purely in the setting of matrices and density operators, density matrices. So that's what we'll be doing in the next couple of lectures. And then we'll go very highbrow, talk about, so until then, we don't have to talk about unbounded operators, but then we'll have to talk about unbounded operators. So we'll develop the appropriate theory and then dive deep into modular theory. All right, any questions?
Yeah, I have one question. Like in the infinite tensor product of sister algebras, that all are isomorphic. That part I didn't get it.
Yeah.
Repeat it again.
So, so here you have M to infinity C, and you have a faithful state. So the representation that you'll get, this pi rho of M to infinity C, this will be a faithful star representation, star homomorphism, right?
Okay.
So the image will actually be isomorphic to M to infinity C as a C-star algebra.
Yeah.
So whatever row you use, the end result will actually just give you the same C-star algebra. But when you take the strong operator closer, things will start changing. the powers factors, those will be different. But when you're just looking at the GNS representation of this scar algebra, the inductive limit, then they're just the same C-star algebra. So I made a pretty big mistake there. So don't so make sure that you don't kind of have it deep in your brain, subconscious, that okay, these two are non-isomorphic. So row 1, row 2. Okay, so does that answer your question?
So, but here we are taking a norm closure, right? In the sister algebra.
No, since it's a homomorphism, so it's automatically norm closed, right? I don't have to take this norm closure, right? So it's a star
Okay.
homomorphism of a sister algebra, so it is automatically going to be norm closed. It's a star
Okay,
isomorphism.
okay.
Yeah.
Yeah, right, yeah.
Yeah.
Okay.
Yeah.
And one more is in between. You were telling that this left regular representation contains all irreducible representation. Like.
Yeah. So
What
that is so left regular representation in at least in the finite group case. So what's the proof? Let's see. In fact, you can give an explicit number for that. So it is what's that formula? So dimension of the this is the main theorem that you have. Let's say you have CG, meaning I'm thinking of CG as being a CG module. So that AA, that is the notation I'm using. This is in fact isomorphic to VI to the dimension VI, direct sum I equals 1 to it. First of all, one of the key theorems is that the number of irreducible representations is equal to the number of conjugacy classes of the group. And the dimension of the irreducible representation is equal to the multiplicity of this irreducible representation in this left regular thing. So VI, so this comes from character theory. So maybe you can take a quick look at any standard references. So character theory, if you look at for finite groups, you'll in fact have you know the multiplicity. VI will occur, the irreducible representation, VI will occur dimension VI times in this left regular representation. So that's why you actually get this formula, dimension VI squared is equal to order of the group. Yeah, where VIs are the irreducible representations. Okay.
Okay.
For finite groups. So character theory is the keyword if you want to take a look.
Okay, thank you.
All right. So if there are no more questions, then I guess we can break for lunch. If you have, you can email me, or maybe next time we'll begin with questions. All right. See you.
Thank you.